All right, discrete math. Well, welcome to the third lesson in chapter 3. We're still talking about the mathematics of sharing. We're now going to look at a new method, which is going to be what's called the lone divider method. So if you remember, in 3.2 we talked about the divider chooser method. We're now talking about what's called the lone divider method. So the first important breakthrough in mathematics of fair division came in 1943. Like I mentioned, we're going to be looking at stuff mostly from 1940 up through 1970. When Steinhaus came up with a clever way to extend some of the ideas in the divider-chooser method that we talked about in the previous lesson to the case where there were three players, one of whom will play the role of divisor and the other two will play the role of choosers. Steinhaus's approach was later on generalized to include any number n players where there was going to be one divider and n minus one choosers by a Princeton mathematician named Harold Kuhn. So, first off, preliminaries, just to get everything sorted out. One of the three players is going to be the divider. The other two players will be the choosers. Since it's better to be a chooser than a divider, the decision should be made randomly. So you roll dice, draw from a deck of cards, etc. We'll call the divider D and the choosers C1 and C2. Step number 1, division. So just like before, the divider is going to divide the cake into 3 shares. So S1, 2, and 3. D will get one of those shares, but at this point, they don't know which one it's going to be. Not knowing which share is critical. That's what's going to force D to divide the cake into 3 shares of equal value. Otherwise, D would probably split it up to where there's a larger piece and then some smaller pieces. Well, the problem is, if you divide it up, then you're probably going to be the one stuck with one of the smaller pieces. So that's kind of the incentive in let's make sure it's an equal split. C1 is going to then declare, usually by writing on a slip of paper, which of the 3 choices are fair shares to him or her. Independently of that, C2 is going to do the same. These are going to be called the bids. A chooser's bid has to list every single piece that he or she considers to be a fair share. In other words, any of them that are worth more than a third of the original cake. It may be tempting to bid only for the very best piece, but this is a strategy that can really easily backfire. To preserve the privacy requirement, it's going to be important that the bids are made independently. In other words, the choosers are not going to know what each other is bidding. Step number 3, the distribution. Who gets which piece? The answer, of course, depends on what pieces are listed in the bids. For convenience, we're going to separate the pieces into 2 types. C pieces, which are going to be the pieces chosen by either one of the 2 choosers, and U pieces, which are going to represent the unwanted pieces that didn't appear on either of the bids. So, expressed in terms of a value, a U piece is a piece that both choosers value at less than 33 1/3% of the cake. And a C piece is a piece that at least one of the choosers, or maybe both, value at 33 1/3% or more. Depending on the number of those C pieces, there are 2 separate cases that we have to consider. Case number 1 is probably the easier of the 2. When there are 2 or more C pieces, there is always a way to give each chooser a different piece from among the pieces listed in their bid. The details are going to be covered in a few examples later on. Once each chooser gets their piece, the individual gets the last remaining piece. At this point, every player is going to have a fair share and a fair division will have been accomplished. So, case number 1. Sometimes we might end up in a situation in which C1 likes C2's piece better than her own, and vice versa. If that's the case, it's perfectly reasonable to assume that they're just going to swap pieces. That's going to make them both happier, and who could be against that? Case number 2 is that there's only one piece, only one C piece. We're going to have a bit of a problem because it means that both of our choosers are bidding for the exact same piece. The solution is going to require a little bit of creativity. First, what we're going to do is we're going to take care of the divider, to whom all the pieces are equal in value, by giving them one of the pieces that neither chooser wants. So in this case, using the visual example, we're just going to have S1 go to D. The remaining 2 pieces. So after D has gotten their piece of the cake, the 2 pieces that are left, the C piece and the other U piece, are then recombined into one piece that we're going to call the B piece. We can revert then to the divider-chooser method to finish off the fair division, where one player will cut the B piece into 2 pieces, the other player then chooses the piece that they like better, and the divider gets the remaining piece. This process for case 2 results in a fair division because it guarantees fair shares for all the players. We know that D ends up with a fair share because they had the original division, so they had fair shares right from the get-go. So what about C1 and C2? The key is that in the eyes of both C1 and C2, the B piece is worth more than 2/3 of the value of the original cake. Think of the B piece as 100% of the original cake minus a U piece worth less than 33.33%. So when we divide it fairly into two different shares, each piece is guaranteed more than 1/3 of the original cake. So let's look at an example of where this might come about. We're going to go ahead and do lone divider with 3 players. So this is going to be case 1. So this will be the easier case to divide between. So we're going to have Dale, Cindy, and Cher are dividing a cake using Steinhaus's lone divider method. They're drawing cards from a well-shuffled deck of cards, and Dale draws a low card, which is bad luck, and also having the name of Dale starting with D was bad luck. He has to be the divider. So Dale divides the cake into 3 pieces. We're going to call them S1, S2, and S3. The next table shows the values of those 3 pieces in the eyes of the players. So with Dale being the divider, obviously he split the cake up to where he believes each piece is 33.33%. Cindy, however, believes that S3 is much higher at 55%, and Cher believes that S1 is higher at 40%. So we can assume that Cindy's bid list is going to be S3 and S1 because those were the 2 that she put above 33.33%, and Cher's bid would be S1 and S3 as well, seeing as those were the 2 that were above 33.33. So the C pieces are S1 and S3. Those were the 2 pieces that were the most valuable. That means that there are 2 possible distributions. One distribution would be Cindy gets S1 and Cher gets S3, with Dale getting S2. But a better distribution, the optimal distribution, would be that Cindy gets S3, Cher gets S1, and Dale gets S2. In the case of the first distribution, what would probably happen is Cindy and Cher would just swap pieces, so there's really no rational reason why they would not do so. Thus, using the rationality assumption, we can conclude that in either case, that the final result is going to be the same. That Cindy's going to end up with S3, Cher is going to end up with S1, and Dale is going to get S2. All right, we're going to use the same setup as in that previous example. Dale is still the divider. Cindy and Cher are going to be the choosers, but we're going to look at version 2. So this is going to be where some things get a little bit dicier. So Dale divides the cake once again, S1, S2, and S3. The next table shows the values of 3 pieces in the eyes of the players. So Dale is still the same. Notice that Cindy, though, is bidding 40% for S2. Cher is bidding 60% for S1. That means that there's only one possibility. This is the most simple of all possible situations. And there's only one possible way you can distribute the pieces. Cindy gets S2, Cher gets S1, Dale gets S3. So, we're going to look at them once again. The whole gang's back from examples 3.2 and 3.3. We're now going to look at case 2, which is the much more complicated case. Step number 1, the division. So once again, Dale goes through the same process, divides the cake, and here is the distribution. So you've got Dale, where it's all 33.33, but now notice that both Cindy and Cher are preferencing S3. Cindy's at 50%, Cher is at 70%. All the other values are below 33.33%. So now their bid list contains just S3. So this is going to be a problem. So first thing we're going to do, the only C piece is S3. Cindy and Cher talk it over, and without giving away any other information, they agree that of the 2 U pieces, the S1 is the least desirable. So without giving away any other information, they decide that S1 is least desirable, which it was for both. That means that Dale is going to get S1. Okay, so now we need to figure out, because they both can't get S3, what's going to happen. So, the remaining pieces, which are S2 and S3, are going to be combined to form a B piece, which is going to then be divided by Cindy and Cher using the divider-chooser method. One of them is going to divide the B piece into 2 shares. The other is going to choose the share that she likes better. Regardless of how this plays out, both of them will get a very healthy share of the cake. Cindy's going to end up with a piece worth at least 40%, whereas the B piece was worth 80% of the original cake to Cindy, and Cher will end up a piece that is worth at least 45% of the original cake. So going back to this table here, basically what that's saying, for Cindy, if you combine S2 and S3, you get a total of 80%. Whereas for Cher, you combine those and you get a total of 90%. The worst case scenario is you end up with 1 being 80 divided by 2 is 40%, and the other would be 90 divided by 2 is 45%. And in either case, you still end up with a piece that's more than 33 1/3%. So in either case, you end up with two people that are happy. Okay, so now, continuing on that, like I mentioned, it wasn't until later that we had a generalization for it. So for a little while, in fact, I think it was a couple of years' time, that Steinhaus's lone divider method was for 3 players. Kuhn was able to generalize it to more than 3 players. Now, the more that there are, the more difficult it gets. So we're only going to give kind of a basic outline here that's going to illustrate the details with a couple examples where there's 4 players. So the preliminary is much the same. One of the players is going to be the divider. The remaining n-1 players are all going to be choosers. As always, better to be a chooser than a divider, so that the decision should be made by a random draw. All right, so the divider D is going to divide our set S into n shares, where D is guaranteed of getting one of those shares but doesn't know which one. Hence, D is probably going to divide those as evenly as possible. Each of the n-1 choosers independently submits a bid list consisting of every share that he or she considers to be a fair share. So this is the bidding. Then the distribution. Bids are listed, much as we did with the 3 players. We'll have to consider 2 separate cases, depending on how those bid lists turn out. Case number 1, if there's a way to assign a different share to each of the n-1 choosers, then that should be done. Needless to say, the share assigned to a chooser should be from his or her bid list. The divider, to whom all the shares are presumed to be of equal value, is going to get the last share that's left over. At the end, players can swap if they want. Case number 2 is like the previous example, the end of it, where we had a standoff. In other words, there were 2 choosers that were bidding for just a single share, or possibly 3 choosers bidding for just 2 shares, or K choosers bidding for less than K shares, if you want to generalize it out to whatever number you'd like. This is a much more complicated case, and what follows is kind of a rough sketch of what to do. To resolve a standoff, we first set aside the shares involved in the standoff from the remaining shares. Case number 2. Likewise, the players involved in the standoff are temporarily separated from the rest. Each of the remaining players, including the divider, can be assigned a fair share from among the from the remaining shares and sit packing. All the shares that are left are going to be combined into a new bounty, S, to be divided among the players involved in the standoff. And the process starts all over again. So, as an example, let's look at where we have 1 divider, Demi, and 3 choosers, which are Chan, Chloe, and Chris. Demi divides the cake into 4 shares, S1 through S4, and then the table on the following slide is going to show how each of the players valued each of the 4 shares. So, looking at this, and remember Demi divided it equally based on her own opinions, so you got 25, 25, 25, 25. So anything more than 25 would be considered a fair share. So for Chan, 30 and 35 here. For Chloe, just 40 here. And for Chris, 25 and 35. So to go through this, just to illustrate how this will work, and I'll explain it on the following slide, you would want to start by looking at Chloe's bid. Chloe only had one choice that she thought was fair, which is S3. So Chloe would take S3. There was another player, though, that had S3, which was Chan. S3 is no longer available, so Chan is going to be kind of stuck with S1. And then going down to Chris, now that 25% is no longer available, S4, which would have been the choice already, would go to Chris, and the remaining piece of S2 would then go to Demi. So really the only player that didn't get their top choice, so to speak, would be Chan. And the only one that he valued more than S1 was S3, so he could try to trade Chloe for S3, but it doesn't look like Chloe's going to be too interested in S1. And so while it might not be the ideal choice for all of them, it would be a fair choice for all of them, being that it was more than 25% of the total piece. So bid lists are open, clear that for starters, Chloe has to get S3. Like we mentioned, there was no other option. Then this forces the rest of it. S1 had to go to Chan, S4 had to go to Chris, and finally we get the last piece to Demi. So, this results in a fair division, although not entirely envy-free, as mentioned before. Chan is going to wish he had Chloe's piece, but Chloe's not about to trade pieces with him, so he's going to be stuck with S1. From a strictly rational point of view, Chan really doesn't have any reason to gripe, though. Like we mentioned, he still ends up with 30%, of which is more than 25 that he was entitled to, so he's still coming out ahead. Okay, let's look at case 2. So let's look at where it's not necessarily possible to come up with an agreeable outcome right away like we did in the previous example. So once again, we're going to let Demi be the divider. We've got Chan, Chloe, and Chris as the choosers. Division, same as before. And now here is the division table. So Demi again stays at 25% each. Chan has a single option that they would like, which is S4. Chloe at 35 and 30% has 2 possible outcomes. And then Chris at 35% only has 1. So now the problem is between Chan and Chris, there is no way to split up to where they each have an fair division. If you give Chan S4, the closest Chris can get is 23%, but that's below the 25% threshold. So we're going to have to do something different. So bid lists are open. We can see that there's going to be a standoff brewing between Chan and Chris, both of which want S4. The first step is going to set aside and assign Chloe and Demi a fair share from S1, 2, and 4. Chloe could either be given S2 or S3. Looking at those, S2 is the preferable option, so we'll go ahead and give S3 or S2 to Chloe. Well, let's see. What are we going to do? Chloe could be S2 or S3. We'd rather have S2, of course, but it's not up to her. Okay, yeah, so she doesn't get any choice. It's just a coin toss. So coin toss is used to determine which one. And so let's say Chloe gets S3, which is kind of bad luck. Demi can now be given S1 or 2, and another coin toss, Demi ends up with S1. The final move, you guessed it, we're going to take S2 and S4 into a single piece to be divided between Chan and Chris using the divider-chooser method. And since S2 plus S4 is worth 60% to Chan and 58% to Chris, if you want to check it, go back to that table and add them up. Regardless of how you divide it out, they're both guaranteed a final share worth more than 25%. Half of 60 would be 30%. Half of 58 would be 29%. So in either case, they're going to end up with a fair division of the cake. All right. Going to talk about another method now, which is what's known as the lone chooser method. So we've had the lone divider method, which was where the divider was kind of by themselves. The lone chooser method is going to work kind of opposite. You're going to have multiple dividers, but only one chooser. So a completely different approach for extending this divider-chooser method was proposed in 1964, so you can see the time difference there, by A.M. Fink, who was a mathematician at Iowa State. In this method, one player plays the role of a chooser. The other players start out playing the role of dividers. For this reason, the method is known as the lone chooser method. Once again, we're going to start with a description of the method for the case of 3 players. So with the preliminaries, you're going to have one chooser, 2 dividers. Let's call the chooser C. Let's call the dividers D1 and 2. As usual, you're going to decide by a random draw. So D1 and D2 are going to divide between themselves into 2 fair shares. To do this, they use the divider-chooser method like we mentioned before. Let's say D1 ends up with a section S1 and D2 ends up with S2. Each divider then is going to divide their share into 3 subshares, which they believe are equal. Thus, D1 divides S1 into 3 subshares, which we'll call S1A, S1B, S1C, as you can see in the picture. And likewise, D2 is going to divide their shares, as you can see in the picture. From those, the chooser is now going to select one of D1's 3 subshares and one of D2's 3 subshares, whichever ones that they like best. The 2 remaining subshares make up C's final share. D1 then keeps the remaining 2 subshares, and D2 keeps their remaining 2 subshares. So, why is this a fair division? How does this work out mathematically? Well, D ends up with 2/3 of S1, and to D1, S1 was worth at least half of the total value of S. So, if you think about what that would mean, if you took the 2/3 that they were given, multiplied by the 1/2 that they thought was fair, the 2's would cancel, they ended up with 1/3 of what they thought was fair. Hey, what do you know? Same would be true of D2, so they would have had the same outcome of 1/3, and C, it doesn't really matter, they got 1/3 of each that they wanted from each group, so they also got 1/3 of the original, which is fair for all of the participants. So, let's look at an example of this. We've got David, Dinah, and Cher, again, whose names are pretty clear on which ones they're going to be. They're going to be dividing an orange pineapple cake using the lone chooser method. Just to give you some numbers to help illustrate how this would work, we're going to say that the cake is valued by each of them to be at $27. So each of them expects to end up with a share worth at least $9. So the individual value systems, which are not known to each other, but available to us as outside observers, are as follows. David likes pineapple and orange the same, so he values them at an equal $13.50 split. Dinah likes orange but hates pineapple, so she's got $27 to 0. And Cher likes pineapple twice as much as she likes orange. So at the beginning, after random selection, Cher gets to be the chooser. Yeah, totally random, right? And thus gets to sit out steps 1 and 2. Step 1 is the original divider chooser. So David and Dinah start by dividing the cake between themselves using divider chooser. After a coin flip, David cuts the cake into 2 pieces. And again, remember, David doesn't care. His is split 50-50, so it didn't matter to him how it got sliced. Now notice that for the sake of evaluating this, that we're making a 60-degree angle with both the different flavors. Since Dinah doesn't like pineapple, she's going to take the share with the most orange, which at this point is going to be valued at $18. Now, here comes the subdivision. David's going to divide his share into 3 subshares that, in his opinion, are of equal value. So all those are going to be the same size. Notice that that's going to be 2 pineapples and 1 orange. However, Dinah is going to divide hers into smaller subshares that, in her opinion, are equal. Remember, Dinah hates pineapple. So she's going to take the orange portion and divide it up into the pieces that you see there. All right, now here's the selection part. Cher's turn to decide which of the subshares from David's 3 and from Dinah's 3 that she wants. She's going to choose the 2 pineapple wedges from David's subshare, one of the 2, and the one with the larger pineapple share from Dinah's subshares. So notice that in the end, what they're going to end up with is that David gets a final share worth $9. He got kind of half and half, which is exactly what he would have wanted, a fair share. Dinah gets a fair share worth $12, and Cher gets a final share worth $14. David's satisfied, Dinah's pretty happy, Cher should be pretty ecstatic. Now, in the general case where there's n players, lone chooser method involves 1 chooser and n-1 dividers. As always, preferable to be the chooser than a divider, so chooser is determined by random draw. Method is based on an inductive strategy. If you can do it for 3 players, then you can do it for 4. If you can do it for 4, you can do it for 5. And as you continue on from that, if you can do it for n-1 players, then you can do it for n. All right, so here are kind of the steps when you're looking at the nth possible case. Step 1, the division. They divide fairly the set S among themselves as if the chooser didn't exist. Step 2, each divider then subdivides his or her share into n subshare. Step 3, selection. C finally gets to do some stuff. C is going to select 1 subshare from each divider, 1 subshare from D1, from D2, and so on. At the end, C ends up with n-1 subshares, which makes up C's final share. And each divider gets to keep the remaining n- subshares in his or her subdivision. When properly played, this lone chooser method guarantees that everyone, dividers and choosers alike, ends up with an equal fair. All right, a little bit longer on that one, a little bit longer kind of fair division game to explain to you guys. We're going to be looking at a few more before we're done with this chapter. I believe we've got one more continuous example, and then we'll look at a couple discrete examples where you cannot necessarily divide up one single asset, where we'll have to talk about how we can divide the assets up a little different. That being said, have a good rest of your day, and I will talk to you next time.